Hello. So many database implementations will allow you to save the contents of the database to a file, which will then be read in order to repopulate the database so data can persist when the process stops. In many database implementations, if you control this file, you could then leverage normal database operations to perform fun things like leaking data, overwriting records, and other fun things. The purpose of this project is to look at several different database implementations, see what can be done if you can write to the database save file, and some general understanding of the inner workings of the different database implementations we look at. Today, we will be looking at the Sqlite3 database implementation. So now a bit about Sqlite. It is interfaced with through SQL queries in the SQL programming language, does not need a server running in order to use it, and all of the demos done in this video were against version 3.39.0. So first up, I just wanted to quickly cover how Sqlite works. Sqlite will take SQL queries as commands and execute them, which is what I wanted to talk about. This will be fairly brief, both due to relevance and I didn't fully look into all of the operations. If you want more details, check out the docs linked below. So Sqlite's first job when it gets a query is how will it, well, it has to interpret it, so do this through a tokenization process. So take this query right here, it will be parsed out as to this and then actually tokenized like that. And eventually through this process, you'll end up with some opcodes. And those opcodes are fed to a virtual machine. That's where the actual work of executing the query happens. Let's go through a quick example. Take, for instance, this SQL query right here. In order to execute this query, these opcodes are executed right here. Now, for this, looking at these first few opcodes, it looks like it's basically just opening up a database as readable and then rewriting it to the beginning. That's because we want all of the records from the database. And then we see these set of opcodes repeated 3 separate times, followed by a halt, which stops execution within the virtual machine. Having this set of opcodes repeated 3 times makes sense because there are 3 rows that are returned. And looking at these opcodes that are repeated, we see that there appears to be 2 instances of op column, which I believe what that is it's grabbing a single column from a single record, which makes sense because each row has 2 columns. Result row, I believe, is putting the columns together to get an actual row that I can output, and next just moves it to the next record. Let's take a look at one more example. Let's take a look at insert into. So we're inserting a single record with 2 columns in it. Kind of similar to the previous one, we see that it has some opcodes to initialize the process. Instead of opening it as readable, it opens it as write. And similar to how for the selection process, it calls op column for each individual column, it looks like there are 3 separate opcodes that are being called here for each of the records. Now I know our insert statement is only inserting 2 columns, but it's also inserting a row ID. Then it will actually make the record and insert it, and then halt execution of the query. So next up, I want to briefly cover the format of a record in SQLite, how the data actually is in memory. Starting off, I'm just going to create a sample table with 4 separate records, which you see right here, and save it to this file right here for us to actually see in a hex editor right here. Now, if we scroll all the way to the bottom, we see the data right here comprises the 4 separate records. Now, this data itself is actually the same data that you can actually see in memory, which I'll show you in a second. But I want to go through this in a hex editor first because I feel it's more viewable in a hex editor. But before I do that, I want to briefly cover conceptually what the layout of a record is. So now for the format of a record, it will start off with this size value right here, which represents the total size of the record. This size value doesn't include these first 2 fields, rather the size of everything else that follows. Preceding that, we have the record ID, which is what I believe is the primary key of the record. In the test databases that I've seen, it's the Is this the first record created, second record, third record? I'm fairly certain, depending on the schema of the database you have, this value will change. Preceding that, we have the actual header, which the header just specifies the actual type of data that the record holds. We'll start off with a size value, which is the size in bytes of the record, including the size value itself. Following that will be an array of various data types, which are values that mean that, hey, after this you'll have an integer followed by a string followed by another integer. Those data type values that we see are right here. A value of 1 means 1 byte signed integer, a value of 4 means a 4 byte signed integer. Now, for strings, there are really two types, blob and text, and these are just any value that's greater than or equal to 12, with blobs being the even numbers and text being the odd numbers. Now, the reason why this is this way, part of the job of a data type is to specify the size of the data, and since strings are variable length, basically the larger this value is, the larger the string is. The actual formula used to calculate the size of one of these strings is we just take the value, subtract 12 from it, divide it by 2, and that value is the length of the string. But preceding the header, we have the actual data as an array in the same order that the data type specified it as. So now let's go back to the database save file, open up it in hex editor to actually review the format of some records for some examples. The first record we see, the size value of the record is 13, and since it does not comprise of the first two values, it starts from right here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the record itself comprises of these bytes right here, and we see this, that the size value of the next record is also 13. Preceding that, we see that the ID is 4, which kind of makes sense since this record was the fourth one created. We see that the size of the header is 3 bytes, so it consists of these 3 bytes right here, with the first data type being a 2-byte integer, and the second data type being a string of size OX1D, which we see, let's see how big that actually is. Oh wait, I did that wrong. It's not divided by 8, it's divided by 2. So we see that the length of the string should be 8. We see that the 2-byte integer is 0x0190, which this should be 400, which we see that it is. Following that, we see is a string that we specified, and then is the beginning of the next record, which we basically see is the same format, but one thing I just want to point out that the ID for this one is 3 because it was the third record created. The next one is 2, and the final one is 1 for the ID. So next up, now that we covered the format of a record, let's actually see this in memory. So for this is still the Sqlite running in GDB, so I'm just going to go ahead and pause it and then search for one of the strings from the record. That way we will hopefully find it. We see that there are a lot of examples right here. All of these I can already tell are not it because they have ASCII characters that follow it. So I'm going to go ahead and try looking at this one. Let's try to clean up the output a little bit. Okay, cool. So we see that the record starts off with 0x0d, 04, 03, 02, which corresponds with 0d, 04, 03, 02, 1d, 01, 1d, 01, followed by 90, which you see right here. And then we see is actually starting right here is ASCII 3, ASCII 5, ASCII 7, ASCII 1, which you see is ASCII 3, 5, 7, 1. So I'm not going to go through all of this, but we can see that this data right here is actually the same data present in this database save file. And one cool thing I'm going to show you about it is I'm just going to add in some bytes to this database save file, reload it, and show you that that data will actually end up in memory. So for that, I'm just going to put dead beef right here, save the file, rerun this, .open, what was the name of the file, record layout. I'm going to select everything from the database. And now let's go ahead and refind the data, which you see starts right here. And we see, okay, because this data, I believe, is stored in Little Indian, the order is a little bit messed up, but we see DE, or actually, B, DE, AD, BE, EF. So it's basically dead beef, but backwards. But we see that the data that we actually wrote to the database save file did actually end up in the memory of the database instance. So next up, I want to briefly cover in detail the layout of a database save file. So starting off, we will have the actual header for the database itself, which will encompass roughly the first 0x64 bytes. So all of these bytes right here, I'm not going to be going through all of these values in detail because I don't feel that is certainly relevant for what we're trying to do. If you want those details, check out the docs linked below. But the important value I wanted to point out is this value right here, which I believe is the size of a page. So Sqlite uses memory paging in order to actually organize its memory for databases. And within the pages, they'll have the page header with the first page header beginning at offset 0x64 and going 8 bytes over here. The first value within the page header is flags. I'm not sure quite what that is. Second is offset to free, which I believe deals with like freed records, not quite too sure. After that, we have a 2 byte size value for the page, which represents the size of the number of effectively records stored within that page. After that begins an offset to where the content first begins. And then there's a single byte value, I believe, that deals with fragmentation within a page. And then after that, we have a bunch of offsets to the actual records itself. For this page, we see that the offset is 0x0FCF. So we go down here to right here, and we see that there is a record that looks like to be dealing with actually constructing the table itself. Not too sure about that in detail, but right after this, we have another page which goes from offset 0x100 all the way to offset 0x1FF. And this page right here is what will actually store the records that we created. We see that the page record is 8 bytes long, so it's these 8 bytes right here. We see that the flags is 0x0D. I'm not too sure about these 3 values. Yeah, these 3 values right here. However, we see that the number of records is 4, which is the amount that we inserted, which is what we expect to be true. And then we see for this next value is the offset to the content, which is 0x0FC5, which we see scrolling down here is where the records actually start. And getting past that, going past the page header, we see our 1, 2, 3, 4 2-byte values, which represent the offset from the start of the page to the record itself. Start of the page is at offset 0x100, so the offset this refers to is 0x1FF2, 0x1FE3, 0x1FD4, and 0x1FC5, which if we go down here, we see that is actually the start of the record itself, 0x1FC5, OX1FD4, there's the next one, OX1FE3, and OX1FF2. And here is where the records are actually stored. And this middle section effectively is like the free space that memory will be allocated to. These offsets will go downward, and the records will go upward into that space. So assuming that we can actually write to the database save file, what fun things can we do? One thing I found that we can do with this database implementation is we can alter our record such that when we query it, we won't actually just get the value of the record itself, but we will actually leak subsequent records, which can give us a record leaking primitive. Now, I'm just going to go over a quick demo of this, basically the same demo that is linked in the docs below. For this, I have a very basic database with only, well, a table within a database that only has 5 records that we can see right here. So I'm going to go ahead and save this to an output file, and let's go ahead and actually take a look at it. So first off, what actually allows us to do this? This is caused by the fact that in the record, there are size values. First off, there's a size value for the entire record, and there's also a size value for the string argument. Effectively, what we will be doing is we'll be expanding these size values to include part of this next record. And for this, what I'd like to do is I'd like to leak the first 3 characters of this 159 string of the subsequent record. How are we going to do that? Well, we'll need to expand the string by 1, 2, 3, 4, 5, 6, 7 bytes. So in order to actually successfully do this and pass all of the checks, there are 2 size values that we need to update, both the size of the record and the size of the string. For the size of the record, we will need to add 7 bytes. 7 plus 10 is 17, which in hex is 0x11, so we can just put that there. For the size value of the string, right now it's encoded in the Sqlite blob format. Right now it's 8, but the value that we need to change it to is 0x2b, which will increase the actual string size from 8 to 15, so you can go ahead and put that there. Now, right now, in this Sqlite instance, it's still running with the original version of the database. So when we query it, we see that it just returns all the records just fine. However, when we try to reload the database save file, we see that when we query the 759 or 753 record, I should say, we actually leak the 159 from the next record. And just like that, there's a brief example of how we can edit a record such that when we query it, we will actually begin leaking the next few records. Also, the reason why there's a new line character right here is because the first byte of the new record is an actual new line character, which we see right there. So another fun thing that we can do via editing the size values within a database save file is we can expand a record into another record and then update the original record and then overwrite the subsequent records, so it is a record overwrite primitive. For a small demo of this, I created a little table with 4 records that we see here and saved it to this file. So let's go ahead and pop it open in a hex editor. Scroll all the way down to records. Okay, cool. For this, I want to update the 6th record and actually overwrite the record with a bunch of 5s in it. How will I do this? I will expand the string, which right in here, the string column is just 5 6s, into the record with a bunch of 5s in it. So for this, the size calculations I did, I'm just going to expand the string by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, yeah, I'm going to expand it by just 10 bytes. Right here, this is the size value of the string 0x17, which encoded as a blob size, I believe, is 6. However, the calculation to expand it to 0x10, I believe, we have to update it to 0x2d. So let's change that. And for this, right now the size value is 9. I'm going to change it to the size value of 0x14. That way it is correctly modeled and encompasses the size value of the new string argument. That being stated, let's go ahead and reload this database file with our corrupted records. Let's go ahead and select everything from the table. We see that when we query the record with a bunch of 6s in it, we also get the contents of the 5 record, which is a good sign. And now let's go ahead and update the 6 record. If this works right, it should also overflow the record with a bunch of 5s in it. I'm going to go ahead and close this. Let's try and select it. Okay, it looks like something got messed up. However, when we actually look in the table or the database save file, we see that the record with a bunch of 5s in it got completely overwritten, except for the last 5, but everything else got overwritten. So by expanding the size value of a record and then updating it, we were able to actually overwrite subsequent records. So the final fun thing that I'm going to demo today that we can do if we can write to the database save file is actually overlap records. What I mean by this is editing the database save file such that when a new record is allocated, it actually overlaps with an existing record and overwrites that old record. For this, I have a very basic table with 3 separate records, and I dumped the database to the save file. So let's go ahead and open it up. So this is going to be a little bit different from the previous 2 demos. So in the page header, there's a 2-byte value right here. Right now it's 0x0fed. This represents the offset to effectively the free memory that hasn't been used. Right now it's 0fed, and if we go there, we see that it's the start of where the records actually are, but everything before that is free. Effectively, what we're going to do is we're just going to move this offset into the actual record section, probably, I think, somewhere around here. Basically, right before where one of the records start. That way, when a new record gets allocated, it will actually allocate it from the records and overlap with it. So for this, I'm basically just doing the same demo that I had in my docs. We're going to be overwriting that value with OX0FF3, which we see going down here. Where is this? It's basically going to be pointed to right here. So for this, let's go ahead and do that. Change this to OX0FF3, save it, and let's go ahead and try to do this. So let's import this, grab the records, and let's try to insert a new record into it. And we see, yeah, there's a new record that got allocated, but the 2 record got overwritten. That is because the new record that was allocated actually overlaps with that. And when we go ahead, let's dump it to another file. And when we take a look at this new file, when you take a look at the page header, when it starts listing the offsets for the various records, we see one starts at FA, F4, but the previous 2 actually start at the same offset, 0x0fed. These are the 2 records that are actually overlapped, and when you go to that offset, we see that it is effectively the 0 record. So just like that, by effectively moving the offset to the free data in the page header into the records and allocating a new record of the correct size, we were actually able to overlap 2 records. So in conclusion, we showed a bit about how Sqlite 3 works and some fun things that can be done if you can write to the database save file. I'm sure one thing many of you are thinking, if you can write to the database save file, can't you already read and write the subsequent records? You certainly can, however the data that you're trying to read and write to might not exist at the time you're editing the database save file, in which case something like this might come in handy. That being said, with the fact that you need to write to the database save file in order to use this, will make it extremely difficult to actually use this in any practical setting. That being said, thanks for watching.